Right, thank you very much. Welcome everybody to the second session of among the Waterloo sessions of the RQI-Online conference. Thank you again for coming. Again, a reminder that this is second session, as you probably know, but there will be more sessions running all the way until April. This morning, I have the pleasure to introduce Mercedes Martin Benito, who only the speaker today, the invited speaker today, but also a friend that I know from back in the day. So it's a pleasure to have the honor to introduce you. Merce is at the Universidad Complutense de Madrid. She's a professor there, and she's going to tell us about charged scalar fields with quantum unitary dynamics and Swinger effect. So Merce, floor is yours.
Okay, thank you very much, Edu. So let's start thanking the organizers, Edu and Rick, for not just for giving me the opportunity to talk today, which is my pleasure, the pleasure is mine, but also for organizing this event, right? Especially in these difficult times. So it's very nice that we can all get together, even though from our homes or wherever. Anyway, so by the way, good morning in water to people in Canada or the States. Good afternoon for people in Europe. Okay, so let's start. This talk is based on a work published in JHEP in collaboration with Luis Garay and Alberto García Martín-Caro. Oops, I don't know how to move slides.
Click on the clicking doesn't work. Try the arrows.
It doesn't work. Ah, sorry. Okay. I don't know how I did it. Sorry. Okay. So this talk will be mainly about fixing the infinite ambiguity that we have when we quantize free field theories on non-trivial backgrounds, mainly about the canonical quantization. As all you know, typically we demand invariance of the vacuum under the symmetries of the equation of the equations of motion, or at least we implement these symmetries as unitary operators in Fock space. And this criterion of invariance of the vacuum under the isometries fixes a unique vacuum in maximally symmetric situations, like, for example, free field theories in Minkowski spacetime, where we have Poincare invariance, or, for example, the sitter that is also maximally symmetric, right? Then imposing invariance of the vacuum under the isometries of the sitter leads to the Bunch-Davies vacuum. But in general, in particular in non-stationary situations, the symmetries are not enough to fix a unique vacuum, to fix the quantization. So the question arises, how can we remove this ambiguity? Well, there is a criterion that has been pushed forward, in particular in cosmology, that fixes partially, although quite a lot, this ambiguity. And this criterion is, apart from implementing the symmetries, the criterion is to demand a unitary implementation of the quantum field dynamics in Fock space. So this is something that I have worked about in the framework of cosmology for both the scalar fields and Dirac fields. And today I will explain you how to impose this criterion in a simple model related to Swinger effect. Okay. What is the Swinger effect? Well, the Swinger effect is a non-perturbative phenomenon of particle-antiparticle pair creation out of the vacuum due to strong electromagnetic fields. Okay, so it's very similar to particle creation in curved spacetimes, though even though here the spacetime is going to be flat, the external electromagnetic field is going to provide a non-trivial background, and the situation is pretty much like in quantum field theory in curved spacetimes. So I will consider the electromagnetic field strong in the strong regime, so that we can work in that regime, right, of quantum field theory on a fixed background. The electromagnetic field here will be considered non-dynamical, fixed. This effect was first proposed already in the 30s by Soter and studied by means of an effective action approach by Heisenberg and Euler. And well, some years later, Swinger provided a complete theoretical description of this effect. And since then, there have been many works on this topic by different points of view, different approaches, such that the effective action method pioneered by Heisenberg and Euler, also the Wigner function formalism, the quantum Blasov equation, canonical quantization, etc. I am going to focus on the canonical quantization approach, okay? And I think it's a very interesting effect because we might be close to measure it in the laboratory. Turns out that the high-intensity laser facilities that are being built around the world are reaching very high intensities close to the Swinger limit where this non-perturbative phenomenon appears, let's say. So I think it's a very interesting as a non-perturbative quantum field theory phenomenon from the experimental point of view is quite appealing. Well, and the situation I will consider is a simple one, is the following. I will quantize a complex scalar field that propagates in a flat background with just a homogeneous electric field, though the electric field is going to be time dependent. All right. So, sorry, I'm just getting confused with the way to, okay, sorry. Okay, there we go. So let's focus a bit more on this ambiguity that we have in the quantization, which is general. So here I just explain it in general terms. Imagine that we have the Lagrangian of a free scalar field theory. From this Lagrangian, and given the space of solutions of the equations of motion that I will call capital S, from the Lagrangian, we can construct as a scalinear form mu that is time independent. And also if our theory presents gauge covariance, we can also construct this scalinear form to be also gauge independent, okay? And then from this scalinear form, we can construct the simplistic structure of the theory, just considering the real part, and regard the space of solutions as a covariant phase space, okay? So this is mainly to fix notation. All right, this at the classical level. Then when we want to canonically quantize this theory, we need a Hilbert space, right? So we need to construct an inner product out of well, to endow this space of solutions to convert it into a Hilbert space. Mu almost verifies almost all the properties that we would like this inner product to verify, right? It is time independent, it is gauge independent, but it fails to be positive definite. So simply out of the Lagrangian of the theory, we don't have enough structure to obtain a Hilbert space. In order to construct the inner product, we need to introduce an additional structure that is a complex structure that I will call J. So we introduce a complex structure such that this object, this scalinear form with J acting in the second argument, turns out to be a positive definite inner product in the covariant phase space, in the space of solutions. Okay, so I continue analyzing a bit more what is this complex structure. It's a real map in the space of solutions. It's actually a symplectic isomorphism such that its square is minus the identity. So J has two mutually orthogonal eigenspaces, one for the eigenvalue plus I and the other for the eigenvalue minus I. So these two eigenspaces allow us to split the space of solutions in two mutually orthogonal contributions. the eigenspace with plus I eigenvalue, and the eigenspace with minus I eigenvalue. For example, in the familiar situation of Minkowski with Poincare invariance, we would call this the positive energy frequency solutions, the sector of positive frequency energy, and this would play the role of the negative frequency sector. When we don't have time translation invariance, we cannot talk about frequencies, but we can still do such splitting, okay? Based on the, as I say, based on the spectral decomposition of this complex structure. And then we take the S plus eigenspace and complete it with respect to the inner product that we have. And the completion with respect to this inner product of S plus give us what we call the one particle Hilbert space of particles. And by convention, we take the complex conjugate of the other contribution, the S minus, and its completion with respect to the complex conjugate of the inner product give us what we call the one particle Hilbert space of antiparticles. And then the direct sum of both Hilbert spaces give us the full one particle Hilbert space. So from this, I think it is clear where the ambiguity leads, because we have the freedom to choose different complex structures, and different complex structures give us different splittings of the space of solutions, and therefore different one particle Hilbert spaces. And these different quantum theories might be inequivalent. So this is where the ambiguity is in the theory, let's say. I will codify it in the freedom of choosing the complex structure. Okay, and then as I said in the introduction, in order to fix this ambiguity that we have in choosing the complex structure, I will demand the quantum evolution of my field to be implemented as a unitary operator in Fock space. So let's understand what that means. I'm going to regard evolution as a canonical transformation in my space of solutions. So let's study this. Given the covariant phase spaces, we can always find a symplectic isomorphism that maps S into the canonical phase space. So we can always move from the covariant description to the canonical one via this isomorphism. So both spaces, both descriptions are completely equivalent. The canonical phase space is simply the space of initial data, right? So we will introduce an initial time, T naught, to identify the covariant phase spaces with our space of initial data. So I will call here in this diagram, phi of x means the evaluation of the field at initial time. And this omega of x means the evaluation of the canonically conjugated momentum to the field at initial time, right? So we can move from S to gamma via this identification. And in the canonical phase space, we can always understand evolution by moving from one Cauchy slice at time t naught to another Cauchy slice at another value of time t. And well, in terms of these symplectic isomorphisms, this evolution, calligraphic T in canonical phase space, is simply the composition of these two maps, right? We would move from Cauchy data at time t naught, we can move to the covariant phase space and then identify this with the data at another time t and move here. And this evolution in canonical phase space in turn induces also an evolution picture, let's say, in the covariant phase space S, right? Here in the diagram is pretty clear. We can also map from phi to some tilde phi that would come from undoing the identification from the canonical phase space to the covariant phase space. And this give us this operator, capital T, in covariant phase space. So at the end of the day, we are just here regarding evolution as a time-dependent canonical transformation in covariant phase space. Okay, this is all classical. Let's see what are the consequences of this evolution at the quantum level, at the level of the complex structure. All right, so remember, in order to define our quantum theory, we have introduced a complex structure in the covariant phase space. Then the symplectic isomorphisms IT that allow us to identify S with the canonical phase space gamma induces a one-parameter family of complex structures in the canonical phase space. Okay, so I will call calligraphic J to complex structures defined in the canonical phase space. And is simply related to our original J by this composition of symplectic isomorphisms. So this is a symplectomorphism at the end of the day. And well, evolution in canonical phase space allow us to see the complex structure also as, let's say, evolving from a complex structure defined at T node to another complex structure defined at any instant of time T, in this way. And also, in turn, the evolution that we have at the level of the covariant phase space, given by this operator, this symplectomorphism, also allow us to, or induces a one-parameter family of complex structures in the covariant phase space S. So at the end of the day, we arrive to this relation between the complex structure that we introduce at the very beginning, that in this picture of evolution is simply the complex structure at initial time. We can introduce this one-parameter family of complex structures and regard, let's say, the complex structure as evolving. Okay, so now I will explain what means to implement unitarily the evolution. This means that we would like our complex structure at initial time and the complex structure at any other instant of time. In this sense, we would like then to define unitarily equivalent theories, quantum theories. All right, and this condition, at the end of the day, it controls the ultraviolet behavior of the quantum theory. Okay. In practice, the way I will implement it is by demanding that the Bogoliubov transformation that relates the creation and annihilation-like variables at initial time with those at any other time, right? Those are related by a Bogoliubov transformation at the classical level. I could demand that classical Bogoliubov transformation to be implemented as a unitary operator in the focus space defined by the complex structure at initial time. This is what I will do later. I will explain more detail. This condition is non-trivial, and it might even happen that we cannot find such a J in our covariant phase space. Maybe there is no complex structure that allows for a unitary implementation of the dynamics. But we always have the freedom to introduce time-dependent canonical transformations and map our covariant phase space to a different one that admits such a J. Okay, so we can play with that freedom. This means that we can transform our field variable doing a time-dependent canonical transformation. The equations of motion, the equation of motion will also change if the canonical transformation is time-dependent, and we can work at the level of a different covariant phase space to achieve what we want, that is a unitary implementation of the dynamics. Okay, I had this little GIF. Well, so let's do it for the case I want to study, that is, as I say, the case of a complex scalar field that I will call phi with mass m and charge q in flat space-time coupled to a time-dependent homogeneous electric field. So this field is propagating in a non-trivial background. And I will work by convenience in the temporal gauge, meaning that since the electric field is homogeneous, in the temporal gauge, the 4-vector potential has no time component, and the spatial components are just time dependent. This gauge is very convenient due to homogeneity. Later, almost at the end, I will discuss about gauge invariance, okay? There is still a residual gauge freedom that I will fix by demanding that the 4 potential at my choice of initial time is 0. So this way, in case of a vanishing electric field, we just recover quantization of a field in Minkowski background. Okay. And thanks to the homogeneity of this problem, we can expand the field in Fourier modes. And even more, Fourier modes can be split in real and imaginary parts, and they decouple, okay? So if we do this expansion, modes decouple dynamically, but further, moreover, also real part and imaginary part decouple. So I will introduce this notation set to either denote real part or imaginary part. So these are already real variables. And both of them satisfy this equation of motion. It's the equation of motion of a harmonic oscillator with time-dependent frequency. The frequency is time-dependent precisely due to the time dependence of the electric field. Okay. And now we can analyze the evolution of this field. After decoupling of all the modes, if I just focus on one of the variables, either the real part or the imaginary part, my canonical phase space is simply formed by this pair of variables. They are canonically conjugated. And now I will write the general solution of the previous equation of motion in this form. So I simply codify the time dependence in this function here. Since we are dealing with real variables, I remind you that this set is already real, is either the real part or the imaginary part of these modes. Then the solution is this plus complex conjugate, okay? And I will, without loss of generality, I will set this initial condition, this theta at my initial time, I set it equal to 0. And okay, in general, we won't be able to solve analytically the evolution because that depends on the time dependence of this guy, right? The time dependence of this frequency is non-trivial, and in general, we don't have guarantee of being able to solve analytically this equation. But that doesn't matter. What I am interested in is actually in the ultraviolet limit of the theory, the limit when the norm of the wave vector goes to infinity, as we will maybe understand a bit more later. And under very mild conditions of the 4 potentials, some conditions of integrability that I am not giving the details here, one can prove that the solution in the ultraviolet limit always has this form. The leading order, the leading term in this asymptotic limit is always this guy, the integral of the frequency. And then the remaining contributions are subleading in the ultraviolet and go as this with this power. Well, I am also assuming analyticity, okay, that the functions admit a Lagrange series. And we can also fix initial conditions. We have 2 initial conditions, right? I will fix theta, the derivative of theta with respect to the time that I denote with a dot, to verify this initial condition that at initial time equals the frequency at initial time. So in other words, at initial time, all these subleading guys are set to 0. I can choose that initial condition. Okay, so we can regard the field variable as evolving from some initial data at t0 to other final at some initial time to other final time, and this will be an evolution operator that, as I said, I might not have the analytical expression for it, but I completely have under control the ultraviolet behavior of this operator, because inside it I have, it depends on theta and derivatives of theta, and I have those under control. Okay, and once we have analyzed and understand evolution of the field variables, now we can introduce our annihilation and creation-like variables. I will ask them to respect the linearity of the equations of motion and also the dynamical decoupling between modes. Or in other words, I will demand my complex structure to be invariant under the isometries of the equations of motion. So it respects the dynamical decoupling. And this operator in red is what is defining my complex structure. This is what codifies the ambiguity that we have in the quantum theory, is the way we relate our field variables with annihilation and creation-like operators. And in general, I will allow it to depend on time. Okay? And this dependence on time is what will allow me to, at the very end, being able to find
Merce, just a quick note,
yes.
5 minutes for the end of the talk, but if you need more time, you can bite a bit on the question time if you need to, but just so you know.
Sorry, I am very, very slow. I am, okay. I will speed up a bit then. Okay, so I introduced this way my creation and annihilation-like variables. I have here these F's and G's. I have the freedom to choose them. And then demanding that the dynamics is implemented as a unitary operator in Fock space is the same as to say that the beta coefficients of this Waterloo transformation are square summable or square integrable in this case. Okay, here I am introducing the Waterloo transformation that relates annihilation and creation-like variables at initial time with any other time. All right, so evolution is seen here as a Waterloo transformation, and implementation of the unitary implementation of the dynamics is just demanding that, as I say, that this operator, the antilinear part of this operator, is Hilbert-Smith. And this condition imposes restrictions in the way we choose the functions g and f. So at the end, what we can show is that the dynamics can be implemented unitarily if and only if I define j and f apart from a phase. So this is just by simplicity I choose g real. Being g real, I have to define it in this way with some function h here, and then f has to have this form, and h has to have this very particular behavior in the ultraviolet. The leading order has to be 1, and the subleading order has to be order k-2. If your complex structure verifies this, then you have guaranteed that the dynamics can be implemented unitarily. Okay, I'm gonna be fast. And another thing is that one can prove very easily that if we have two different complex structures that verify these conditions, right, that they respect the isometries of the equations of motion, and that they allow for a unitary implementation of the dynamics, then it can be proved that they define unitarily equivalent theories. Or in other words, this criteria fixes or give us a unique equivalent class of Fock representations. And in that way is what, in this way, we remove the ambiguity. We don't remove it completely because we still have infinite Fock representations, but at least we know that they are unitarily equivalent, okay? For example, one might wonder what happens with the familiar quantization based on adiabatic vacua. Then one can prove that those vacua define theories that belong to this class. one might also wonder what happens with the quantization based on the Minkowski vacuum for this case. It turns out that the quantization based on the Minkowski vacuum, when the electric field is non-zero, does not belong to this class, okay? So does not allow to implement unitarily the dynamics because the subleading term for the corresponding age doesn't decrease as fast as we need. And let me skip this. Just a few words on gauge invariance. Well, here gauge transformations are not symmetries of the system because the external field is non-dynamical, but still the equations of motion is gauge covariant in the sense that if we do a gauge transformation of the field in this way, so this transformed field solves the same equation of motion, but with this other transform for potential. And we have the freedom to choose our field variable. That's why I chose the temporal gauge that was convenient, but now you can wonder what happens in other gauges. Well, in other gauges, the only thing we have to do is once I have the complex structure for the case that I am interested in, if we gauge transform via some gauge transformation capital J, then in the transform covariant phase space, the complex structure that we have to introduce to quantize the theory is given by this guy. This guarantees that both theories are physically equivalent. This is at the level of the one particle Hilbert space. At the level of the Fock space, I am not implementing gauge transformations as a quantum operator. I simply regarding them as classical rescalings, as time-dependent rescalings of the field variable. So this has to do with that freedom I said at the beginning, that we have the freedom in doing time-dependent canonical transformations of the field variables. So gauge transformations would be an example of that. And well, just to finish, we have seen that the criteria that dynamics is implementable as a non-trivial unitary operator in Fock space, together with invariance of the vacuum under the classical symmetries, fix a unique equivalence class of Fock representations for the particular case of a charged scalar field propagating in a flat background with a homogeneous time-dependent electric field. All these representations lead to a particle number density of created particles that is well defined at all instants of time, okay? So this is what implementing the dynamics unitarily means, that the number of particles created out of the vacuum under evolution is finite at finite time. We have also seen how to, once you introduce a complex structure for a particular gauge choice, how we should change the complex structure in another gauge fixation in order to have physically equivalent theories. And finally, there still remains an ambiguity in the quantization. And for that, we need extra criteria. If we want to select a unique vacuum within this equivalent class, then further criteria are needed. Well, this is everything I wanted to say. Thank you very much for your attention.
Thank you very much, Merce. Very good talk. We're gonna proceed now the same as in the last session. So you don't have the power to unmute yourselves, but if you have questions, I would ask you to use the raise hand feature. It should be under reactions. And I'm gonna go and give permission for you to unmute yourself one by one. And if you have extra questions and somehow can't find that button or that option is not there, I will give some time at the end of the questions for you to ask. All right, we have the first question from Chris Fuster. Chris, I'll give you the power to unmute yourself now.
Thank you very much indeed. Thanks, Mercedes. You didn't mention Hadamard states in your talk. Can you tell us if the states that you obtained from your construction are Hadamard?
Yeah, thank you for the question. Indeed, we do need to, we have the expectation that they are Hadamard, or better said, that Hadamard states also belong to this class. But indeed, this is a very good point that we would like to investigate further to find the relation between this simple criterion, let's say, and Hadamard condition. Also.
Yes, indeed, because if you want to do more than just talk about particle number density and get to Wick squares or something, then you eventually need to go to Hadamard class, I think.
Indeed, we suspect that Hadamard states would lead within the class like fulfilling further criteria, right, regarding renormalization properties, etc.
But you could say, why not start with Hadamard?
Why not?
Why not just go directly to Hadamard?
Yeah, well, we just seeing this as a complement of the familiar studies based on Hadamard that I mean, it's not that we are, I don't know how to say, but it's just maybe a different point of view at the end to get to the okay. to move to the same direction, right?
Okay, thank you very much.
In the case, also, okay, this comes from a long path. Let's say the first scenarios where we applied this was in cosmology, also in the context of quantum cosmology. And there, when we do, I mean, we do quantum field theory on quantum spacetimes in a way. And there, in that context, we do need to identify very clearly what we call background and what we call field. And for that, we might not be able to rely on properties of this structure that you would call background, because in that context we are working with quantum entities. Anyway, it comes a bit from that story.
Thanks, that's helpful.
All right, thank you very much, Chris and Merce. Next question. Anybody? All right, if for some reason you're unable to raise your hand, you have the power to unmute yourselves. So unmute yourself and ask.
Well, in the meantime, I'm going to ask a question. Mercedes, thank you so much for the introduction regarding the QFT in curved spacetimes or general. That was very enlightening. No, I would actually like to see the example slide that you sort of skipped there regarding the particle number creation, because I was very interested in that, to be honest.
These plots.
Yeah. It looks like you did an example for a specific choice of the electric field, right? Yeah,
this case is analytically solvable, and it was already analyzed in the literature in terms of asymptotic states. This is an electric pulse. So we have an electric field that in the asymptotic, in the distant past, in the distant future vanishes, and there it is meaningful to define asymptotic states. So here we only wanted to show that, yeah, asymptotically we get the same results as they were obtained before, but that we can also compute the density of particles at any instant of time. Still, I mean, this is for a particular choice of complex structure, which would correspond to h equal to 1. But we have a whole family for other choice. The curves might be a bit different, but asymptotically all will lead to the same result, of course. This is all this is detailed in the paper, okay?
All right. Thank you so much.
All right. If there are no further questions, I'm gonna ask myself one. So Merce, that's super cool. I'm not super, so two things, I guess. One is a follow-up to Chris's question that I had. I was the question that I had in my mind is like, I was wondering if you were to demand Hadamard, right? Maybe that actually restricts the vacuum further as you need, no? I mean, I was thinking maybe that's a condition. That's the condition one misses to remove that the extra ambiguity.
Yeah, no? I guess so, right? That if you impose Hadamard condition, I would suspect you restrict even further within this class of theories. Yeah.
And I kind of share the, I mean, from the point of view of QFT, of course, I kind of share Chris's perspective that maybe that's the reasonable thing to start with, right? I mean, because I want to do physics. I mean, if I consider this a quantum field theory, I want to do physics with it, and I want I need to Hadamard condition. Yeah. Anyway, another question I have. I'm not so surprised though that that the Minkowski standard choice wouldn't work, right? Because you don't have any more Lorentz invariance here, so you have a potential. You don't have any reason to expect that would work, right? Or am I missing something?
No. And this was already well known, of course, that Minkowski vacuum does not allow for this unitary implementation, but still sometimes you take papers in the literature and they base the quantization in Minkowski vacuum.
I see. Okay. Well, then it makes sense that you say it, right? There's the and then finally, I guess this is more about the Swinger effect, which is something that's always Swinger effect in itself. I think again, I don't know how much applies to the talk here. So the Swinger effect is usually described, right, in the privileged frame, if you want, where you can talk about a constant uniform electric field. I was wondering, because I've never seen it myself, and this is just my ignorance, and maybe you can ask this question. In a covariant description of the Swinger effect, in which, of course, you don't have to choose the privileged frame, right? And you can explain the Swinger effect in an arbitrary frame. What would that be like in terms of interaction? It's difficult for me to conceive of above all because it's a non-perturbative effect. So it's very non-trivial to me to imagine what it'd be like. Do you have any intuition there, or?
I don't think so. Yeah, like we are also moving to more complex situations. And yeah, here I just dealt with this simple case where we can impose homogeneity. But no, I completely agree with you that no, we have to think further also.
I mean, that's I think every time that I've seen it, to be honest. It's just a question I always ask when people talk about the Swinger effect. All right. Maybe a final question out because I have the time. Is it one-to-one? So I missed it. You probably said it, but is it one-to-one? The condition demanding so is it one-to-one the condition about the finiteness of the sum, the integrable, the beta being square integrable? Is it if and only if, or is?
Yeah. For this condition of unitary implementation of the dynamics, it's if and only if is actually, because I speed up. We can write the condition. I'm looking for the slide in this way also. What we want is this difference to be Hilbert-Smith.
Right.
And this means the whole tower of Bogoliubov transformation for all the modes in whole Fock space. And it's the same to say that, mathematically speaking, that the betas are square integrable.
Yeah, because I know one way certainly works, but I didn't know the other way as well. So it's nice. Okay, very good. I don't have more questions, and there's 1 minute for a very quick question if anybody else wants to ask anything.
Well, I do have another question actually. So the full background that you gave in the beginning regarding QFT and curved spacetimes and stuff, like general QFT and how to relate the classical theories with the quantum ones using the covariant phase space formulas and all that, that's all general. So is there any analogy that can be drawn between this specific model that you solved and a gravitational model, maybe with a time varying metric?
Yeah, sure. It's exactly the same actually. You know that, well, I chose this. Yeah, that was completely general. The thing is that we have a non-trivial background, non-stationary background. In the case of gravity, it is provided by gravitational field. Here, that role is played by the electromagnetic field. But all this discussion I gave here general is general. For example, in cosmology. In cosmology, we see it all the time, you know, that if you have a non-stationary universe, then the same applies. The field evolves in time, etc.
Yeah, but I mean, the sense that like, no, yeah, sorry, I think I wasn't clear. The thing is like, in the end, you looked at this specific model, which was an A of t coupled in the Klein-Gordon equation, essentially, right?
Yeah,
with
well,
the complex field.
Yeah, for example, in cosmology, coming back to the example, at the end, the equation of motion I dealt with is that one, no, the typical equation for a harmonic oscillator. For example, in cosmology, you might start with, I don't know, the Mukhanov-Sasaki field. You can find a rescaling. Typically, if you start, let's say, cosmology, the equation of motion for your minimally coupled field has also friction terms. but you can introduce a rescaling that is a time-dependent canonical transformation to map your equation of motion to this form. But then you quantize a different field variable. And that's the idea. You play with that freedom to quantize the field variable that it is more convenient for you. And if you work with the one that verifies this equation of motion, you can find then complex structures that allow you to implement unitarily the dynamics.
Right,
No,
thank
well,
you.
in cosmology, typically we define the Mukhanov-Sasaki variable, and it has a 1/A rescaling that is actually doing this.
That makes sense. Well, thanks for the example.
We run out of time for questions. Thank you very much, Mirte. That was a great talk. And as usual, a pleasure to have you.
Thank you. Thanks for your attention. Very nice seeing you all.
Likewise. I hope things are okay within reason in Madrid.
We are okay.
All right.
We are coping with the situation.
Right. Okay. Let's move to the next speaker. So if you could share your screen, I'm gonna. Rick, can you unmute the next speaker, please? No, I see. Now it's unmuted. Okay.
Hello, everyone.
Oh, we can hear you. Okay, now you have to check if you can share screen.
Does it work?
It does. Okay. So.
Okay.
All right. So, all right. So if it's all ready, I'm gonna. Are you ready for me to introduce you?
Okay. Thank you very much.
Right. So hold on. Let me introduce you. You deserve an introduction.
Okay. Sorry.
Our next speaker today is again, Polish names are tricky for me. Let me try. Kasper Dębski.
Yes, it's good.
Okay, from the University of Warsaw. Is going to tell us about the Casimir effect in conformally flat spacetime. So, Kasper, floor is yours.
Thank you very much again. My name is Kacper Dębski, and today I'm gonna talk about the Casimir effect in conformally flat spacetimes. My presentation would be based on the recent paper published among the others with my supervisor Andrzej Dragan, and this work is available in open access. So if you are interested in this topic, please look at it on the internet. Today, my talk will be structured as follows. I would like to start with the basic introduction to the Casimir effect in the standard way. Then I will talk about the generalization of the Casimir effect to the non-inertial frame of reference. And in this section, I will talk about the one particular example of a non-inertial frame of reference, so-called Rindler spacetime. Lastly, I will talk you a little about our generalized method based on the conformal anomaly from the general theory of relativity. But this derivation is more technical. So if you are interested also in this topic of our paper, then please look at it on the internet. Okay, so the story with the Casimir effect begins in 1948 when Casimir published his paper. He showed that there is a non-zero force acting between two plates in a vacuum. It's a very strange effect, and what's the reason of this strange behavior? One can think that everywhere there is the same vacuum, so from the simple symmetry argument, it's nonsense. But the truth is not so simple, because this vacuum inside the cavity between the plates is different from the one outside the vacuum, the plates. And every state inside the cavity consists only of standing waves. So there is a discrete family of modes inside. And on the other hand, the state from the outside can consist of the solution of arbitrary frequency. And as a consequence, it means that these two plates change the total amount of energy in the space. We also know that the energy of the vacuum inside the cavity is given by this kind of sum, of all possible discrete frequencies. So the result is as here. But however, the energy stored in the region before we introduced the plates was given by the integral over all possible frequencies. So the increase of the energy due to the plates has this simple form. And based on this consideration, it's quite obvious that the force acting on the one plate can be defined as the minus derivative of the energy with respect to the distance between two plates. So this is the standard famous Casimir force. It turns out that it's not the only correct method that gave the right result. In 1956, Lifshitz showed that the Casimir effect can be understood as the effect of pressure acting on the plates from the inside and from the outside of the cavity. So he showed that for every quantum field, we can introduce the energy momentum tensor in the same way as for the classical fields. And the force acting on the plate can be written as the expectation value of this tensor projected onto the direction of the force and onto the normal to the surface of this plate. And in this case, there are the same vectors denoted here as small n. And the only difference between these formulas is that we are using different states. So to evaluate this whole expression to get the result. And then finally, the force acting on the right, for example, right plate is given by just P1 minus P2, and the result is exactly the same as for the Casimir method. Okay, and now my main goal would be to show you how this simple equation can be derived for a non-inertial system. But introducing non-inertial motion adds a new layer of complexity to this whole problem because it's not a standard situation. One of the simplest example of a non-inertial frame of reference is a so-called Rindler frame of reference, as I said before, that describes the uniform acceleration. But before we will talk about the more exotic spacetimes, we have to clarify some basic definitions and understand how they translate into more measurable quantities, like, for example, force. Okay, so let's introduce Rindler transformation. The transformation between the Minkowski coordinates and the corresponding Rindler ones has this kind of form, where this parameter A defined so-called reference hyperbola. And now the coordinate time tau is the proper time measured along this reference hyperbola. And the general form of the tensor metric in this Rindler spacetime can be written as this. And we can notice that the proper time flows differently on different hyperbolas due to this G00 component of the metric. And it would be very important in the future of our derivation. Okay, and in our considerations, we will be talking about the accelerating cavity of the length L. It means that the plates move in such a way that at any time the length between the distance between two plates are the same in its rest frame. So from the perspective of the observer moving with the cavity, the length is constant and equal to L. But from the perspective of the standing observer, the Minkowski observer, for example, the plates will be moving along the hyperbolas that have the common event horizon. So from the perspective of, from the perspective of the Rindler coordinate system, this cavity is stationary, what is obvious, I think. Okay, but to fully characterize this system, we are also introducing two parameters defining the distance of the plates to the event horizon, this capital A and capital B. I think it's worth noting that at time equal to 0, the plates are at rest in both coordinate system, as you can see in this small simple picture. Okay, we just defined the system, so now let's talk about quantum field. Exactly the same as in the introduction, we are considering a massless scalar quantum field governed by the Klein-Gordon equation, and this equation can be solved in the free space, and the solution then has this form where letter K denotes any real number. And then using this kind of solutions, we are decomposing our field operator in this simple way, where HC means Hermitian conjugate as always, and AK and AK dagger are the standard bosonic operators. So and in addition, we are defining the vacuum annihilated by every operator A, and we are denoting this vacuum as capital theta in the ket, and this vacuum play the role of the vacuum 0 outside from my introduction. Okay, and we can also construct this kind of solution of the Klein-Gordon equation inside the cavity. In this case, we impose the Dirichlet boundary condition, and such a solution has the form of generalized standing waves. And here index small n denotes all natural numbers. So using this, by using these solutions, we can construct the field operator as follow. And now this field operator is decomposed into the discrete family of modes. And then the same as previously, operator B and dagger are bosonic operators. And for such operators, we have an appropriate vacuum denoted here as ket with 0 inside. And this vacuum plays the role of the vacuum 0 inside from the introduction. And at this point, I think we are ready to recreate this Casimir's procedure of deriving Casimir force. But first of all, we have to define the energy in the case of general relativity. And in this place, we can use the symmetry of the Rindler spacetime, because we know that the Rindler spacetime has the time-like Killing vector, and existence of this Killing vector means that the Rindler metric is exactly the same for every time tau. And then from the Netter theory, such symmetry gives us a conserved quantity, which we call energy. And so the energy is then defined as the integral over space of this expectation value of the energy momentum tensor, and small h in the square root is the determinant of the induced metric in the space area. In our case, it's for the Rindler's metric, it's just one, but I would like to emphasize that this general structure of this quantity. because it also works for different geometries. Okay, and in this definition, the vector n is the mentioned timeline killing vector, the tau, and the vector small v is the unit normal vector orthogonal to the surface of constant tau, and is also proportional to this the tau. And this form of energy came from the Gauss theory, but written from the general curved spacetime. So I think it's pretty obvious that is the correct form of the conserved quantity, which we are called energy. And exactly the same as in the introduction, we are looking for additional energy in the system due to the plates. So we are defining the increase of energy exactly as follow. And then the force acting on the plates are given by this kind of expressions by the derivative of the energy with respect to the position of the plate. I remind you that A is the position of the left plate and B is the position of the right plate in the Rindler frame of reference. And we can see that for the left and for the right plate, the result is different. But I think it's not very surprising because these plates are moving with different accelerations. So it's pretty obvious. I would like to emphasize that this result depends on A.
Casper, you know, the 5 minutes to the end of the talk. Of course, you can bite a bit into the question time. Just so you know, it's 5 minutes.
Okay, thank you. Parameter A is describing the Rindler parameter transformation. So it's not any physical quantity. So it's strange that this result depends on this A. But now it's time to use a Lifshitz method. And as you remember, his idea was based on the concept of pressure from the vacuum. And one could be tempted to define something similar to the previous formula, but by using the spatial killing vector. However, no vector generates symmetry of this Rindler space, so we are not equipped with another formula analogous to the one for energy. On the other hand, an inertial observer is equipped with a pressure formula associated with a killing vector from the Minkowski spacetime, just normal the x. So we can follow an alternative approach. We can identify the Casimir force by the inertial observer sees when the cavity rests in its frame of reference with the force by point-like dynamometers attached to the plates. And the construction of the Rindler coordinates indicates that these quantities are equal at time equal to 0, because at this time plates are at rest in both coordinate systems. So from the inertial observer point of view, a field pressure acting on the right plate can be written as the energy momentum tensor contracted with the spatial killing vector from the Minkowski spacetime, denoted his this capital N. And now this small v is orthogonal vector to the plate, so it's d chi. And then the formula for this force is just P1 minus P4, P2. And finally, it ends our second derivation. And we can see that this force has this form. And what's more, let's note that this final result, is different from the one derived by using the Casimir approach. We will analyze these differences, but now let's think about this time dependence of the force in the Minkowski spacetime. Okay, so according to our method, we know that the force acting on the cavity in its rest frame has this simple form shown on the previous page. And now we can ask the question of how this force looks from the point of view of another inertial observer. And by using Lorentz transformation from the cavity rest frame to the inertial observer system, we can recreate this strange hyperbolic cosine function in this two force. So it means that this cosine function from the perspective of the initial observer is just the consequence of the Lorentz boost. Okay, so now let's compare these two equations. We derived two different formulas for the Casimir force acting on the accelerating plates, and the main difference between them is that in the first formula there is an A in the numerator and B in the denominator, but this A is absent in the second formula. And in addition, there is also a B square in the denominator of the second one. So one can ask me a question, which one is the correct one? But to answer this question, I have to remind you that in the Casimir's approach, we used only the coordinates time tau and chi, and it means that the first formula for the force can be understood as the derivative of the force with respect to the coordinate time tau. But we can find the force acting on the second plate with respect to the local time on this plate. And we can write that the derivative of the momentum with respect to the local time measured in the second plate is proportional to the derivative with respect to the coordinate time with some factor equal to the square root of g00. And fortunately, this expression is exactly the same as for the Lifshitz method. So it means that we can repair, we can fix our first formula to get exactly the same result as for the Lifshitz method. And we also
technically out of time, but you bite me into
okay, maybe 2 minutes, okay? And the next argument, which can prove that this fixed formula is correct, is the limit of gained for small acceleration. So we can easily see that that this formula has correct limit for standing cavity. So because this recreates this famous Casimir formula. Okay, and if my time is gone, so I can stop here.
Oops. All right. Thank you very much, Casper. So in these talks, just for you and for everybody, it's a compromise between how much time you bite into the question times how much question you want to have.
Okay, I understand.
All right. Perfect. Thank you very much, Casper. Appreciate it. Good talk. Let's now, if the other questions, please raise hands. All right, there's one question from Jorma. Jorma, you can unmute yourself now.
Hello, very nice talk. One question, maybe you said this and I just missed it, but what was the state of the quantum field that you assume outside the accelerating cavity?
Outside, it's a Rindler's vacuum. So I would like to talk about it later, but my time is gone. So if you wish, I can show you some more slides. And here we have some observer that is stating in the accelerating racket, which is very long in comparison to the cavity. And this observer measure vacuum, so it's a stationary Rindler vacuum, and then this observer can measure this kind of derived force, Casimir force, by this small dynamometer in the wall.
Thank you.
Thank you very much for the question.
I feel really bad because we stopped before the nice cartoon.
Yes.
So I don't know if Rick, do you have a question?
I mean, I would like to know if there has been any progress in generalizing this for arbitrary, either arbitrary reference frames or non-flat spacetimes, which is, I mean, it's in the title of your presentation, right?
Yes,
how to go to
yes,
conformally.
We propose the generalized method based on this conformal anomaly, and we know how to generalize this derivation for any conformally flat spacetime. I don't know whether it is possible for general spacetime, but for conformally spacetime we have this formula.
All right. Well, thank you very much. We maybe have time for one more question. Short. Well, if there aren't any more questions, thank you very much, Casper. Really nice talk. Thank you for your talk.
Thank you very much.
All right. So we go to the next speaker. You can stop the recording. Tell us what we set up. So, Jörg. All right. So our next speaker is Jörg Smitsmeier from the Vienna Center for Quantum Science and Technology. He's going to tell us about quantum simulating relativistic quantum field theories and what we can learn from experiment. Very cool. Remember in this talk that you can write on the slides. So
yeah. If you have questions, you can write on the slides. Yeah.
All right.
And point out all the I usually give talks to learn something new and find mistakes. Yes. So thanks for having me, because I'm coming from a completely different community, but talking a lot to Bill and lately Bill Unruh and others about quantum simulating these things. I found that there are many things that we did over the last 10, 15, 20 years and thought about it might really fit into here. And so maybe I just give a quick overview and then an homework at the end of what, as a viewpoint of an experimentalist, of what you can do and what I would require for experiments to be, how they should do and to be able to believe them and what they can do. So what's the goal? As an experimentalist, I would like to, I'm not as strict as Bill Phillips. Bill Phillips would say if it doesn't happen in lab, it's not physics. Yeah. And, he did good with it. He got the Physics Nobel Prize on implementing laser cooling. But I would say that for me, it is always, physics really happens in the lab. If it's a good theoretical description, you have to be able to do it in a lab in some way. And of course, there's many things that which extremely difficult to access. And but quantum simulations can help us to build, quantum simulators for that. And the question is, how good are these? Now you can do quantum simulations, and that would be a completely different talk. You can do quantum simulation by doing, trotterization of your equations and then simulate it. Or you can do build an exact analog of the system and then try to simulate it like an analog computation. What I'm thinking about here is something, in between. It's some kind of an emerging quantum simulator that we think are much better to do it, because, if the thing turns out to be in a correct and nice way and can be verified, then it's basically some kind of RG flow from a microscopic Hamiltonian into a quantum field theory, and then you can be, you can have the power of emergence to really build models that might be very, very good models for this type of physics. And what I was interested from the beginning is, can I make inflation, or can I make a decay of the false vacuum, and things like that. And lately we worked with Bill, and I think Bill will talk about it, about how you could detect the Unruh effect in some of these quantum simulators. So what's the rationale behind there is also that many of these effects that I would be interested in are based on quantum field theories in various space-time geometries. And so, you can go straight for like very complicated thing, but I think, as an experimentalist, you have to go step by step. And the first thing is that, can we build quantum simulators for field theories? And as a first step, try to probe, can you apply them? And what are the limits and how they are applicable? And the simple thing is, of course, in flat space-time. So what's our way of basically try to build this type of simulators? And they're based on the relation between quantum many-body systems and their quantum field theory description. Quantum many-body systems, I think, are really ideal starting point for building such quantum field theories, the complexity of the many-body wave function is way too large to be able to observe it in all details. In fact, you can only measure few body observables, and maybe Sebastian will also tell you in the next talk, that we can measure 10 body observables, and then we're basically limited by the computational complexity of analyzing our data. That really forces you to make a coarse graining, and coarse graining reminds you of RG. And the question is that within the RG framework, this leads to a really effective description of the system. And this effective description of the system can be very, very different from the microscopic physics. Yeah. And so a natural way of describing this type of many-body systems are these emerging effective models, and most of them can be written down in field theory. Now, the question is, can we build interesting field theories from these many-body systems, and how good are these emerging quantum field simulators? Yeah, and when and really, and how do they break? Do they break down, logarithmically? Do they break down exponentially? Do they break down polynomially? That will depend on, I think not much is known about these things. Yeah, there's a natural way to probe these models, and that's through correlation functions. And the question arises, which quantum field theory did I really simulate? And in the next talk, Sebastian will tell you something about how to really extract the parameters of an effective field theory directly from experimental data. So how do you distract the Hamiltonian and its quantum corrections, its effective action, running coupling constants and vertices and things like that? And we can do that now directly from our experiments. So what would be now the way how to do it? You take a quantum many-body system. How do you want to build such a relativistic quantum field theory? You take a quantum many-body system where the effective description has excitations that look like a relativistic particle. That's now the hand-waving experimentalists' argument. These things are very well studied in solid-state physics over the last 50, 60 years, models like that. And there's a huge, big, thick book by Terry Jamaki about the 1D physics, especially done in 1D physics. And in that models, of course, the quantum many-body system at zero temperature would be the vacuum state. And the conjecture is that the low energy physics relates to a relativistic quantum field theory. Example of such a typical excitation spectrum would be Bogoliubov excitations in a quantum gas. That's why I will tell you afterwards mostly about experiments in the quantum gas, but there are many other systems. You can think about, areas of superconducting qubits. You can think about surface wave in superfluid helium, and take systems and you name it. But the article quantum gases have an enormous amount of way to control things. Yeah, and of course the caveat is at very high energies, this linear dispersion relation breaks down, and that basically means that at the UV you see the microscopic physics behind that effective field theory description. Now, the question is, how far does these analogs really go, and what can we look at? And there is lots of things I will tell you about light cones and things like that now in experiment. There's a lots of theoretical work now how you can really get this analog that goes as far as looking at the Lorentz transformation of temperature and things like that, and Casimir effects, Unruh radiation, and things like that. So for the experiments, I would like to basically show you first what is the system that we study. And one of the systems is the 1D quantum gas that's related to a latential liquid, which is has an excitation spectrum, which is light-like, it's phonon-like. Or you take a two tunnel coupled 1D quantum gases that has excitation spectrum, which is like a massive relativistic particle, and it's a Sine-Gordon model, and show you how to probe it. And then I will give a quick rundown of what things you can measure. You can cut the quantum field in two and look what excitations you get from cutting the entanglement of the quantum field. You can look how they relax after cutting. How fast does the system know that you have cut it? Yeah. How does that information spread throughout the system in a light cone? I can show you that if this cutting is not infinitely fast, you can create really funny quantum states, which have strange parameters, and it will be interesting to see and say a little bit about the St. Gordon model and maybe about recurrences. So what's a quantum gas? What's the system we look at? So as I said, the physics of 1D systems is one of those where people over the last 60 years developed this type of models that you could think of using for quantum simulating relativistic quantum field theory. Now we are not in we're living in 3D. We're not living in 1D, and so we have to make a 1D system. And so typically you take a gas of these radical atoms, you put it in an harmonic trap, yeah, and then you have a very weak longitudinal confinement here. You have a very weak longitudinal confinement, and you have a very, very tight confinement in the transverse direction. And what's important is that the interaction energy and the temperature should be smaller than the transverse excitation, so that you basically never have transverse excited states. And what would be very important, that this first excited state here, that's populated with vacuum basically, because it's empty. Everything sits in a ground state. And that will be important to look at in our cutting experiments. Then if you take that in there, you can write, such a quantum field as having an order parameter which has, a thermally populated phase and a thermally populated density population. And what is nice is that this thermally populated phase is very easily to be measured in experiment. And you can really probe that in that way. Why is it interesting? Basically have for the perfect 1D system, you have the Lieb-Lininger model, which is an integrable solvable field theory. But the Lorentz effective field theory for that model is an Lattinger liquid. Its excitations are sound waves, has a linear dispersion relation, and that's a direct model for a relativistic quantum field theory. If you take two 1D systems, the effective model that you can derive is a St. Gordon model, which has excitations with a mass and which has topological excitations. And depending on the size of this initial parameter here, it can have weak or very extremely strong correlations in the model. So it has a very, very broad range, and we can implement that basically in 1D physics and build it in the lab. Yeah. How do we do that? You need a platform, and that's my only slide where you see anything how real an experiment looks like. So we do that we build it on a chip because we want to have something that's extremely robust. And to make a long story short, with these chips, you basically can switch on your experiment, and it works, and you can do thousands and thousands and tens of thousands of experiments to really do statistical physics and build statistical ensembles and to look at the properties of these field theories. And you can get these atoms into this regime where you're really in this 1D system. And what's very nice is you can very easily split such a system into two, and by that measure interferences. And over the years, we developed all these methods that basically generalizes the homodyne and heterodyne measurements of quantum optics into measurements where you basically interfere two fluctuating systems, and how we can extract the properties of our system there. So in an experiment, what you usually do is you have an experiment, and then you want to know what's the result from this experiment. So what you do is you can apply some kind of unitary operator, and you do some imaging, and then you do an evaluation, and you extract the values. Now, by now we have tools where we can see every constituent in the quantum many-body system. So what we basically do in the imaging, we make a projective measurement of the many-body wave function in the position basis. And what that relates to the experiment depends on which unitary operator here I implement. If I implement time of flight, then I measure momentum, for example, or different other things. Yeah, and so in that sense, what is also clear is that in these images there is way too much information, and we can never get everything out. So what you usually do, you have to evaluate and extract values from the measurement. And one example would be, you take this interference, these two quantum gases, you interfere them, you measure an interference pattern, You take a single slice out of that, you take the data, make a fit and extract the phase. Now, if that's a Sine-Gordon experiment, this phi of set is the value of the Sine-Gordon field. And that's a really nice, quantum measurement that we worked out together with Fabian Essler from Oxford and Yuri van Nieuwkerk as his grad student at the time. Now, if you have that, you have to analyze the data. You can either make it with correlation functions or make it with full distribution functions, and then you can extract information out of the system. So first experiment I want to show you, what is if I take a field, a quantum field, and I cut it into two? What is happening then? So what do? You take an initial quantum, say you take an initial quantum system, which is a one-dimensional quantum gas here.
A quick note that you have 5 minutes left.
Yeah, okay. Then you split it, and that splitting makes an identical copy as good as quantum mechanics allows you, and then you look at it. What is now nice in there, what you see is that you have the symmetric mode of these two split systems has a thermally populated initial state. And the antisymmetric mode is connected to the first excited state of the untrapped particle, and that's populated with vacuum in the beginning. Therefore, anything that goes into this antisymmetric state is something that gets populated by that splitting process. And the antisymmetric state is exactly that one that I'm measuring the interferences. So by doing that, I have the chance of really measuring things, what's happening to quantum vacuum in that type of systems. And what we see, to make what we see is that you measure that you find that the system reaches a finite temperature, and that finite temperature is given by basically by the parameters of the quantum field theory, the ground state parameters of quantum field theory, which are related to the density and the coupling strength. And you can, as you see here, depending on, it's really nice parallel to the scaling with the density, and it's totally and you see that it's totally independent of the initial condition of the symmetric state. So you really have a nice simulator of what's happening if you cut a system apart. What's also interesting is that this whole process is related to something it came from a completely different direction in heavy ion physics, which is pre-thermalization. And you also see that you basically have, you can measure quantum noise in these systems to a very high accuracy, because the additional noise that you have is very, very small. Now, if you do that, what you have is that in the beginning, when you split, you have long-range order in the system, and when the system starts to know that it is split, it shows a thermal-like correlation function. And the question was, how does this long-range order transform into thermal-like correlation function? And you can see this very nicely on in the correlation function itself. And what you see is that in all these experiments, you see that you have some kind of a point where there's a point in which moves out in space, and outside the specific point, you have a long-range order. Inside, you see the final correlation function. So if you would be a one-dimensional being that sits in that quantum field, in that vacuum, and he sees, the splitting happens, what he immediately sees afterwards, locally, at this local point, he sees the final correlation function, the final temperature, and sees an horizon expanding throughout his universe, so that it's basically showing coming in there. And we can do that, we can extract that back, we can measure that, and it's exactly the sound velocity. Now that experiment corresponds exactly to what Calabrese and Cardi predicted for conformal field theories to happen a few years before. The next point is that what happens if you really go and not split infinitely fast? Up to now, it was just a cut. You split very fast. If you don't split infinitely fast, but you split slower, you find that these correlation functions look very strange. And usually, if you see the fast splitting, you have this non-translation variant correlation function. You have an autocorrelation, which is 1, and then you have an exponential decay going down here. But what you see if you split slow is you have an enhanced correlation, which has to be imprinted outside the light cone into the system, and this has to be imprinted in that splitting process. Now we can look at that in more detail by analyzing the correlation functions in more detail, and we find out that what we have is we have some of the modes in some of the quantum field excitation modes are much stronger excited as you would expect from quantum noise, and there's a series of modes here and out here which are very strongly suppressed, and these modes basically are squeezed modes. And so I think there's a nice way of going into that, and we are basically currently trying to find out how strong you can squeeze this mode, and what can you learn, what can you play with type of mode. So you have very strongly number squeezed modes in there, and so you can play some interesting games, I think, with these quantum fields depending on how fast you cut. And
you're technically in your question time, which is fine. I mean, you just bite in from it. But
yeah. So I'm basically I'm very soon I'm done. Just want to say, so the Sine-Gordon model, I can be a little bit quick in there. Is that then, and Sebastian will talk about that more detail. So, but it's a nice way of seeing how these field theories emerge. You have a microscopic Hamiltonian here. This microscopic Hamiltonian, is a very, very involved microscopic Hamiltonian. And then you do, following Gritsel, Polkovnikov, and Demler, they made many different approximations. And so if you do a whole series of approximations in there, you end up with a Sine-Gordon model. Now, what was interesting in there is that these approximations basically threw away everything that was more than second order. So when we started to see that, we wanted to see, how good is this quantum Sine-Gordon model? How good is this effective field theory? A description of this microscopic Hamiltonian, and we can implement it very nicely in that, and we can basically externally evaluate all the parameters of the model. Now, what we did is we measured correlation functions and measured high order correlation functions, and what turns out is that even though the derivation only took into account terms of second order, up to 10th order, and here I think I show up to 6. I show up to 8th order here, but we can extract up to the 10th order connected correlators, and which means that these are all the non-perturbative sums over 5 body interaction that cannot be divided into lower order interactions. So it's really at the very, very high order of correlation are perfectly related to the Sine-Gordon model. So even though that this derivation was, didn't take any of these higher order things into account, it seems to be that derivation looks into that this emergence of the Sine-Gordon model is much, much better than you would expect. And yes, and another interesting thing in this quantum field theories is that you can observe recurrences in the sense of Poincaré. And how can you do that? You can do that when you design your dispersion relation and when you design your spectrum of the excitations. And so one example is that if you take your system in a box, the spectrum of the excitation is such that you would see the long range order coherences to come back. If your transverse confinement, if a longitudinal confinement is a harmonic trap, it doesn't have the correct dispersion relations, and it doesn't come back. And if you do that, really see that in an experiment, that you basically, have you could basically get the original quantum field state back in here. Now, how can we use that? And we can try that. I think that's interesting. And it's not only that the second order correlator even the, and what's more interesting, that even the higher order correlation functions and the vertices and the measurement of the knowledge about the vertices and all these other things from original strongly correlated system can come back at a specific time. And it's just a paper that came out last weekend in Nature Physics. So good. What have we learned? I think outer-cold atoms are a good system to quantum simulate relativistic quantum field theories, and such intricate effects like what happens when you cut a quantum field, the dynamic of light cone and emergence of the final state of in a light cone like evolution. You can make interesting quantum field states when you make slow cuts, and you can implement the Saint-Gordon like quantum field theory, which has massive excitations and topological excitations. You can look at many of these things, and if you have recurrences, that allows you to look at quantum fields in long times, and the correlation functions give you an good insight into that. And there's up here is a series of papers basically where we worked on that over the last years. Now the question really is, how far can you push that, and how will it break down, and how much, and how will it break down? That leaves me basically to some homework, which I think as an experimentalist I always like to pose. If you come to visit my lab, you always get a list of questions to follow up, and so the question is, for the homework for the theories, how much can we push these quantum simulators? And we first have to do that for flat spacetime, because only then can we have confidence to simulate more general spacetimes. I think it's I don't feel very comfortable if I don't understand flat spacetime to do something with much more general spacetimes. We know how to implement externally imposed general spacetimes. That's by density, which is related to the sound velocity, and where beautiful experiments were done by for the Hawking radiation, for example, by Jeff Steinhauer on that. Big question is that can we implement dynamically created spacetimes? I think then it will get interesting, and we have to see. But I think there are also ways of maybe implementing what we heard in the first talk, and we're talking with a few people how to implement in the Saint-Gordon model. You could implement pair creation if you can make a massive Saint-Gordon model, and we're working on it how to implement it. That would give you a handle direct in the lab to look at pair creation in a Schwinger-like model. Good. So that's our part, and yes, that leaves me. And let me leave with the homework questions.
Okay, thank you very much, Jörg. Thank you for the talk. Very nice. It's really nice to have experimentalists talking at the RQI conferences. I can tell from the point of view of a theoretician, it's nice to see people who actually do things.
You should invite more.
Yeah, I know. So we have time for one question, perhaps, before you have to run. There are two questions. We have one from Alison, and my one went first. They look to be simultaneous in my reference frame. So anyway, I'm going to go with Alison because it appears first. And let me give you the power to unmute yourself. Alison, you can unmute yourself.
Hi, I hope my question's a really quick one. You talked about measuring correlations, and I wondered what you could say about what kind of correlations they are. Are they necessarily just classical correlations, or are you also potentially measuring quantum correlations, and how can you tell the difference?
That's a very good question. So, the measurement of correlation is basically, you could take your picture that you have before, and then you choose which type of correlation you want to measure. And if you could measure density correlations, then you would come up with a 1,000-point correlator, and that you can never evaluate. If you take, for example, that, you would come up with 1,000-point. Each dot in here is an atom. Now, what you in the end do is that you go up and take these phases, and that suddenly this evaluation gives you another field, which is that the phase field phi of z, and you have that at 40 or 60 or 80 points. And then it's up to you which correlation you calculate. Yeah. And then it's up to you which, it's like if you take, photon counts, the experiment Anton did for the Bell's inequalities, you write in two completely independent computers counts on there. If you want to get out quantum correlations or only classical correlations, depend on what you do with that thing that's written down. And it's the same thing here. It's a little bit tricky here because we can measure one quadrature component extremely good. The other one is much more difficult, but we're currently working on extracting, entanglement entropies and things like that from that. Now, give me another, 6 months. And then we can show you entanglement and hopefully area laws and volume laws and things like that in these quantum field theories.
All right. So we had this simultaneous question by Maxime as well. Thank you, Alison and Jörg. Maxime, can you go fast before Jörg has to run to the doctor?
Yeah, thanks. I don't want to keep you for long. I was just wondering about these dynamically created spacetimes which you're talking about. I mean, what do you really mean there? Do you mean something that's different from a GPE equation? Like,
yes, so something that you would like in GR. So it depends on your the spacetime depends on your mass distribution, and the spacetime is not externally imprinted. Yeah. If I make a GP, everything I do with the GP is I have an externally imprinted spacetime, and then I do the physics of the excitations on top of that spacetime. But these excitations don't change my spacetime. Whereas in regular gravity, these excitations are the planets and the sun and the black holes.
I mean, sure. So you're talking of back reaction, but then what if we let the spacetime dynamically evolve once we've created it sort of arbitrarily? What if we have a pulsed experiment instead of a continuous wave experiment?
Maybe, I don't know. We should think about it. But it's, for me, the question said, how do you separate what things that are imposed from the outside and what things that are dynamically created? And I think there's very, very, very little is done in that. That's why I posted as an homework. And if you have ideas, anytime, we can discuss. That would be fantastic. I mean, these are things that we discussed a lot. We discuss a lot over coffee and wine and things and dinners. And if we can have dinners again.
Yeah, maybe we will.
Hopefully, yeah.
Thank you, Jörg.
All right.
Okay.
So you probably have to run.
I have to run.
Thank you very much.
I will be I can listen to and on my mobile phone, but I will not be able to probably do something meaningful feedback or something. Yeah.
Very much appreciate.
Okay.
I'm gonna tell if people have more questions, maybe they can ask after the next talk.
Sebastian is good. He was involved in most of these experiments, so he also knows a lot of these things.
All right, wonderful.
Yeah.
Thank you. Let's thank Jörg again. Thanks a lot.
Okay, then.
All right, so now we're gonna go to the next speaker. So if you can, the next speaker, Sebastian, if you could check that you can share screen.
I cannot yet.
Oh, now you should be able to.
Yes. Let's see.
Yeah. Also, thank you, Alison and others that reminds us to keep recording. It's a non-zero probability that we will forget, so that's appreciated. We're not gonna stop the recording because we're going.
Can you see my screen? Can you
yeah,
see
we can see it. Okay.
Great.
All right. So our next speaker is Sebastian Ern from the Technical University of Vienna, and he's gonna talk about extracting quantum field theory descriptions from experimental data. We look forward to hearing more of that. So, floor is yours. And I don't know what's going on, but there's some flickering on the screen.
Oh, no. Oh God. Okay, Bill knows this problem.
Okay, now it feels fine. Just let's try. Let's give it a try.
Yeah, it's a bug in KDE / Zoom.
Yeah.
They don't interact well with each other.
If it gets too bad, let me know, then I can try to switch computers.
It's not too bad for now.
Okay, we'll see.
On his screen, everything is fine. On our screens, you get flickering.
Yeah, so you have to let me know when it gets too bad.
I will let you know, certainly. All right,
Okay. Thank
floor
you.
is yours.
Okay, thanks for having me. It's nice to be here and get to know everybody. And thanks, Jörg, for the great overview. That gives me some more time to talk about extracting quantum field theories descriptions from experimental data. For me, it's always, I take a more general approach to say, okay, we have lots of many-body systems in the world, and if we look at them at large scales, we find similar structures in all kinds of different systems, from fish to cyclones to galaxies, swarms of birds, non-equilibrium universality. So everywhere we look, if we just zoom out a little bit and don't consider singular constituents, we see a lot of structure evolving. And so one of the questions is, so how do we go from one, which is usually very simple to describe, we write down Hamiltonian, we can usually calculate everything very simply, to a few where things become more complicated, to a lot of constituents where in the many-body limit, things like the Hamiltonian many-body eigenstates often play a less significant role, since they're anyway experimentally not really accessible. So it's better to phrase the problem in directly observable or accessible quantities, which are usually, as you also said, correlation functions. Now, the nice thing is we know that any quantum field theory is completely described by its correlations, which now over 70 years ago was done by Schwinger. And now we're going to turn the whole thing around and say we have a system, we can measure correlation functions, and we want to know how well can we actually describe or reconstruct the theory, the underlying theory that describes the system at a certain scale. Okay, so I didn't make an outline. I'm first going to do a quick overview of quantum effective actions, renormalization group, and correlation functions. So we're used from classical theory that we have a classical action and we can use a variational principle and we get our nice classical trajectory. Now, in quantum field theory, all of this becomes more complicated, but we can write down a so-called quantum effective action, which then, similar to the classical action for classical systems, gives us the full quantum trajectory simply by variation. So this quantum effective action is then usually the classical action, which is S of phi, plus all quantum corrections that are usually the hard thing to calculate. So this gamma phi especially contains all the quantum and statistical fluctuations. So for example, thermal fluctuations of the system. And it contains all the information, for example, about phase transition, the original classical action, or emergent symmetries of the system, and so on. So usually we could say if we know gamma phi, we solved our theory. So since what we access in the experiments are correlations, quick recap of correlations. So in theory, as probably everybody knows, we usually define generating functionals. So here's the hierarchy of these generating functionals for correlation functions. So we can start with usual endpoint correlation functions, which are just given by the path integral, and we introduce a source j such that we get a generating functional z of j. And if we now do derivatives with respect to j, set j to 0, we exactly get all our endpoint correlation functions. Now, these correlation functions usually have, as I will also, a lot of redundant information, since we usually contains a connected part and a disconnected part. So here, for example, for the 2-point, contains separated 1-point functions. So in the language of Feynman diagrams, it's just simply all completely disconnected Feynman diagrams are irrelevant information and don't give you really any new information at a given order. So to get rid of all this redundant information, we can just take the logarithm of this generating functional z, and define a new generating functional W, which is now the generating functional for this connector correlation function. So if we calculate now a certain order correlation n, we really just get this relevant new information at this order. So then in the next step, what is usually done is that one goes to so-called one-particle irreducible correlation functions. And these are now the fundamental building blocks of all correlations. So if I know my one-particle irreducible correlation functions, I can construct any correlation out of them, and they're usually not further reducible in information. So for the propagator, it is very simple. It's just the inverse of the second order correlation function, and it's usually connected then to the particle, so to the effective mass m of the field. This for the 4-point 1pi correlator, things become a little bit more complicated, and already here I'm neglecting, for example, 3-point interactions, since otherwise it's a lot of diagrams to draw. So for this 4-point connected correlation functions, we can write it as always a full propagator coming in or out, and some true interaction gamma 4, which is now is the proper vertex, which is really then the running coupling constants of the theory that we're interested in. So we can do the transformation now again from Z to gamma to get the effective action. So this is a full hierarchy of invertible transformations of these generating functionals to arrive at the quantum effective action. Now, if we have this quantum effective action, we can write it in a general form, where here this gamma n are these quantum vertices, and order n describes n-body interactions. So order 2 is the propagator, order 4 are 2-body interactions. And we have here then the appropriate number of fields, and we take some non-vanishing background field which we evolve, which could be a false vacuum, or in the case of phase transitions. So one important thing is that all these higher order couplings are dynamically created. So even if the bare action only has 2-body interactions, these gamma n's will usually be created up to every order. Usually at some order n, they become irrelevant, but the problem is that it's usually hard to say, are they irrelevant or not, because they're all non-vanishing. That's basically the same as saying that the Gaussian distribution is the only one that only has a variance and all higher order correlations vanish. If one higher order correlation exists, there's an infinite number of them. And as I said before, these gammas now are really now the momentum dependent running coupling constants that, for example, are also measured in fundamental theories like QED or QCD. So that is nice, but so far we only shifted the problem to some incalculable quantum effective action, gamma phi. So what did we really gain? One nice thing we gained in theory is that there's a whole apparatus, namely the renormalization group, which enables calculation of these momentum-dependent couplings beyond perturbation theory. And for example, this is the flow equation for this quantum effective action at a given scale, which is taken here in the form of functional renormalization group, which is an exact flow equation. So we take gamma at some very high cutoff lambda, where it is just a bare action, and now we can evolve it down to some infrared scale and arrive at the effective gamma for large scales. And this is exactly the trajectory where our effective theory comes in. So gamma, our microscopic theory might be very complicated, and now we go to larger scales and we end up with such an effective theory, which not necessarily, or which, for example, for the same microscopic theory, we can have the same large scale structure or large scale description of the system. Okay, so far that's all basic quantum field theory. Now, one thing that is very different in these experiments is, so commonly quantum field theory is phrased in unequal time correlations. So we have this unequal time quantum effective actions, we have unequal time correlation functions. And on the other hand, usually especially in cold atom systems, what we study are equal time correlations. So as Jörg said, you prepare the system, you let it evolve for some time, then you take a picture, and this usually destroys the system. Now, one thing is that, okay, we know that any state rho at a specific time is completely determined by all its correlations, by all equal time correlation functions. So we can write down an equal time generating functional for correlations, which is directly connected to the density matrix of the state. So at this specific time, we can fully characterize the state by the equal time correlation functions. And now, one nice thing that was done by, for example, Christoph Wetterich in the late 90s is that we can actually formulate all of quantum field theory in this equal time formalism. So we start from a general state rho, we can define our generating functional for correlations, we can write down a generating functional or a quantum effective action at equal time. This is now T is now an index. And this gives an infinite hierarchy of coupled evolution equations for all our vertices. So the problem is, in theory, it is not really clear how to truncate the series, which is why this wasn't really further developed theoretically. But for us, it is very nice to know that if we know all equal time correlations to at every time, we also have a full description of the system. Okay, now we come back to analog quantum simulators. And Jörg already introduced the system, so I don't have to go over it. That is very nice. So I'm starting here just simply with the Hamiltonian, and what I'm considering is exactly this, this two one-dimensional Bose-Einstein condensates in a double well potential. So you have this one-dimensional interacting Bose gas, and you have this tunnel coupling J. Now, as Jörg described, you can do this bosonization and derive the low energy effective theory, which for this system was done by Gritshev and Pokolnikov. And you end up with a Hamiltonian, which you do perturbation theory, the second order in these density perturbations and phase gradients. And we have
Sebastian, just to know, it's 5 minutes to the official end of the time, but again, you can bite into the question time if needed.
Okay, a little bit. Thanks. Okay, so we have some different terms. So we have the quantum pressure term, which is usually neglected. So this would lead to the bending up of from the phonon-like to the particle-like branch in Golubow theory. Then we have here this relativistic free field theory, which is the Tomonaga-Luttinger model. And we have this interaction term, which together then gives us the Sine-Gordon model. And for now, I will just concentrate on this Sine-Gordon model. And to make easier connection with quantum field theory, we now rescale this Sine-Gordon model in this form, where delta rho is the canonical momentum, phi is our Sine-Gordon field, to canonical form. And we get two expansion parameters. So one is this epsilon q, which then comes from the generalized commutation relations. So our fork gamma, where this gamma is defined on the next slide, plays the role of h bar. So if this epsilon q is much smaller than 1, we're in the regime of classical field theory. And we have an epsilon thermal, which plays the role of the inverse temperature. So we know if both epsilon q and epsilon thermal are much smaller than 1, we expect a tree level approximation of the classical field to be correct. Now, the nice thing is, if we're down in this regime where tree level approximations are valid, these momentum dependent vertices exactly correspond to the Hamiltonian parameters. So we can actually measure the Hamiltonian of the system from correlation functions. Okay, so yeah, okay, let's say we now measure this general endpoint correlation function. And as I said before, so we get rid of this redundant information. So we take the connected part, which now contains all the genuine new informations, which are particle interactions if n is bigger than 2. So for n equals 4, for example, 2-body interactions. For n equals 6, it's a generalized 6-body interaction. And you always have to think about that this is also given in a certain time resolution, or basically over all summed over all frequencies, since we're looking at equal time correlators. So it's the combined sum of all 3 particles in, 3 particles out interactions. Whereas in this disconnected part, we would, for example, just have simple propagation without interactions, or for the 6-point, there's the 4-point interaction vertex, full interaction vertex in there, which we already took care of. So for the next 3 slides of results, some useful jargon. So as Jörg introduced, we have these 2 one-dimensional condensates, and what we look at is this relative phase. And we have a couple of scales which are important. So one is the thermal correlation length, which leads to fluctuations of the phase. We have this phase locking length, Lj, which restores the phase and couples it and drives it towards the same. Then we can find this Q parameter, which defines the relevance of interactions in the sine-Gordon model. So it's exactly the prefactor of the cosine term. And experimentally accessible, this is one-to-one related to the observable average cosine phi, where phi is this relative phase. So we can say, okay, this is between 0 and 1, where 0 corresponds to Q equals 0, and 1 equals to Q towards infinity. And we have this gamma, which defined this epsilon Q, for which the classical approximation is valid, which is just a Lieb linear parameter of a 1D Bose gas, which defines the strength of the 1D interactions. So as expected, for weakly interacting Bose gases, we expect the classical approximation to be valid. Okay, so I might need another 5 minutes.
Yeah, so I was telling you, technically in question times, now your choice. How much question time do you want?
5 minutes, then I should be through. So as you said, we can now look at higher order connected correlation functions, and we've defined this measure Mn, where for technical reasons, it's a little bit different than it's usually done in field theory. So we take the sum or the integral overall, the absolute value of the connected part, and divide it by the absolute value of the full correlation. So if this is 0, the connected part is 0, and we basically have a free field theory. If this is 1, all the information, so all amount of correlation is in the connected one, and the theory is strongly correlated. So we start with average cosine phi of 0, where the cosine term in the sine-Gordon model is absent, so we expect it to be just a free relativistic field theory. And we see consistently that, for example, here M4, M8, M10, so up to 10th order correlation, these measures actually do vanish. So we have a slight offset here because it's not an unbiased estimator, but within finite statistics, we see that it actually vanishes. So here we now see that we have a free field theory. Consequently, also for the very strongly coupled, while the prefactor of the cosine is very small, very large, the field itself is very much confined to the center of the potential. So fluctuations are also Gaussian, but here with a finite mass, as we will see in a second. And in the intermediate regime, we have now really a strongly correlated field theory, which is the full sine-Gordon model. So the blue one is some data out of equilibrium, which is connected to sine-Gordon solitons. And I'm going to skip this now. So now we're coming to really measuring these quantum vertices. And one important point is, since we don't have coupling between canonical momentum and the field, the inversion of the propagator is possible even for the limited information of just measuring one quadrature of the field, because the 2-point connected correlation functions is block diagonal, so we can just work with the phase variable itself. So now we have this gamma beta for a thermal state, and we can write it as beta h, which is a tree level, or where h is the bare Hamiltonian of the system, and we have the general quantum corrections that now include everything. And we now did some numerical simulations of the classical sine-Gordon field using transfer matrix formalism, and did some calculations up to one loop correction of these effective vertices in the sine-Gordon model. And you can see that so if we increase this Q, so we go towards a very large prefactor of the cosine, but the field itself gets small. So we actually expect for large Q that tree level becomes better. And this is exactly what we see. So we're very close already to the one loop correction. And if we now go to in the strongly correlated regime, so this Q of 4 would correspond here to some really in the strongly correlated regime, we see that we get strong deviations. So there's really higher order corrections play a role. Now, we had looked at this preliminary at the experiment, and we find very nice results. So for one, if we look at the full 2-point correlator propagator of P and P prime, we can see that we have very good momentum conservation. So we only get, if P is equal P prime, we have non-vanishing values. For all the other ones, they are within statistical error 0. And if we compare now the second order vertex from experiments to theory, we find good agreement, where here we're basically limited by the size of the system in experiments. Now for the four vertex, we can do this similar deconstruction, where now we take this full connected correlations and multiply it with 4 times the inverse propagator. And we do this in the experiments. In the theory, again, we calculate this 4-point correlation. And we see, first of all, that for large Q and high momenta, we get very good agreement with the tree level result, which are then exactly our Hamiltonian parameters. So going to smaller Q and smaller momenta, we again see the change in gamma, which is exactly this non-trivial P dependence, which comes from looking at larger scale. Here's the same for the 3 lowest momenta as a function of Q. And we can see that for large momenta, we basically converge towards the tree level result. And in comparison to the experiment, so we could estimate the 3 lowest momenta in the system with statistical significance, and we see that we are in good agreement with the Sine-Gordon model. We have strong corrections based as compared to the tree level result, but all in all, the data fits very nicely. And one first application of these non-equilibrium, so one first application out of equilibrium was done in Prüfer et al. In Nature Physics, where they looked at this 4 vertex near a non-thermal fixed point, where gamma 4 is based scaling relations, and the system is strongly correlated in the non-perturbative regime. So this really helps. These are really situations where then experiments really can help advance theory, because it goes beyond things that are actually calculable in theory. And with this, I want to thank all the team, especially theory collaborators from Heidelberg and now Innsbruck, and the experimentalists Thomas Schweigler and Bernhard Rauer, who did most of the experiments, especially Thomas. And with this, thank you for your attention.
Thank you, Sebastian. Very nice talk. All right, we have 3 minutes, 3 minutes for questions. If you have questions, please raise your hands now. Seems that there aren't any questions. Well, I'm gonna give you ability to unmute yourselves in case you're having trouble with the raise hand, just in case. Now you can unmute yourself and ask. All right, well, I mean, now I feel bad that I rushed you. All right, so if nobody has any questions, then let's thank Sebastian again, and let's thank all the speakers again for the session. I know it sounds a little bit, I don't know, missing flavor when I clap, because I'm the only one who has audio, but you have to multiply by 50 or so. All right. Thank you very much again. Let me remind you before we leave that we will have another session next Wednesday, and also that at the same time, that's the Waterloo session, and we will have another session tonight at 7 p.m. EST again, which will be the Australian session. That's I'm not sure if I'll be there, but pretty sure that Rick will be. Right. Other than that, I think that that's it for today. Thank you very much for coming to this RQI-Online conference, and I'll see you again either. Well, I will definitely see you next week. All right. Thales, Rick, you should stop recording.